Yes, please good. The other video had problems with it. He was saying something, so in a very quick one. 30 minutes will be out of it. Okay, so good morning. Okay, so where do we 84. Right. So what do we start with? We start with a single line diagram. You need to be able to know what the single. Personally, I think this is how the exam will be, right? You're giving a scenario. When you're giving a scenario, you're required to draw a single line diagram for it. And then when you draw the single line diagram, you find protected elements in the single line diagram. And then some of them obviously require calculation. So you do the calculations for them and propagate it in the system across. Understand? So what kind of elements do we have? So when we talk about a generator or alternator, we represent it by this. Sorry. When we talk about a bus, we represent it by this. When I talk about a circuit breaker, represented by this is one of the most important elements. When we talk about a transformer, represented by this. You understand? Then finally, when we talk about a load, it's represented like this. When we talk about a motor, it's represented like this. It's beautiful. So I'm going to give. Hey, talking too fast. So I'm going to give a situation. I'm going to give a question, and then when I give the question, you can we'll draw the single line diagram for. So let's say that in a certain power system in the country, we have a hydroelectric generator. We have a hydroelectric generator, right? And the hydroelectric generator produces 40 MVA at 14.4 kilovolts, right? The second one is that we have a step-up transformer, right? Step up, which works at 14.4 kV slash 161 kV. The third one is a sending end high voltage bus at 161 kilovolt. The fourth one is a long transmission line of 100 kilometers at 161 kilovolt. The fifth one is a receiving end bus. Receiving end high voltage bus at 161 kilovolts. The next thing is that we have a step down transformer. We have a step down transformer which is 161 slash 11 kV, right? And then we finally have what do you call it? Four 11 kilovolt motors, right? In parallel. And then finally we have various loads or 11 kV. We have various loads in that system. So how do we represent this? Right. So we have a generator. Right. When we get the generator now, in between any two elements, you have to place a protection there so that if a relay needs to isolate it, it can isolate it alone, that is no unit tripping, or isolate it with another relay to isolate the unit, that is unit tripping. Understand? Okay, so we have a generator here, and then we have a step-up transformer. Right, a step-up transformer, 14.4 kilovolts slash 161 kilovolts. Right, and then we have a circuit breaker, another circuit breaker here. We have sending end high voltage bus, right? We have another circuit breaker, a long transmission line. And after the long transmission line, we have a receiving end transmission line here. We have a step down transformer. After the step down transformer, we have another circuit. Right? Then finally, we have our motors and loads. We have all motors inside, then we have various loads. So we have M1, M2, M3 for load 1, load 2. You understand? So this is how our system is, and then you have to name it, right? So 14.4. Right? It is voltage levels that we are looking at. So 14.4, 14.4 to 161, 161, 161, 161 to 11, 11. Then you have your things here. You understand? If there's another step down to 415, you step it down again. So this is our system. This is how we. So if any question given, you must be able to draw your single line diagram. You must be able to know. Maybe he gives us two generators. You know how it's done. He gives us another system. Right? You need to be able to represent that well. You need to be able to represent that well. Okay, so the second thing that we want to talk about is that we had an entire system, right? So let's say that we need to protect our entire system. We need to start from our generator, move to. Yes, so I'm sorry, we had some interruption. So back to it. So we have to start from the generator, and then we move from generator protection to transformer protection to bus bar protection to transmission line protection to industrial motor protection, and then finally to normal loads. Okay, cool. So these are all the protection we're about to look at. Right? So this is how I believe the question will be. Giving a framework, right? And some maybe it has parameters inside and you have to calculate for things. So some of the relays need calculation. Distance relay will need the calculation. So I feel like transmission line is always the easiest. So let's work with okay, bus bar is the easiest. So let's look at the bus bar first, and that's when we'll take it away from the board. Right, so bus bar. So how do we protect the bus bar? Bus bar is very simple. Differential protection. And then I'm sure you can. What just happened? Differential protection. So differential protection, right? We have differential protection, and then finally we have frame earth protection. What is differential? What is frame earth? Right. So for differential protection is how differential protection works is very simple. It works on the principle of it works on the principle that your as a quantity that you measure before an element, right, should be the same that you measure after. So we have a bus bar here. Let's assume this is a bus bar, right? And then we are feeding it some power and we're taking out some power. The power at this point be the same as the power at this point, right? Like basically the same. Of course, maybe like there might be losses and things. So you adjust for that with a factor. You understand? So if I measure here, let's see, this is A1, this is A2. If I measure at A1, A1 should be equal to A2, and it doesn't matter what I'm measuring, either voltage or current, right? When we do differential protection with voltage, it's called the balanced voltage protection. When we do it with current, it's called balanced current or circulating current. So how does it work? So how it works is that at A1, we'll set up a CT, and at A2, we'll also set up a CT. You understand? We want to do balanced current, right? To set up CTs at both sides, and then we'll put a relay in the middle here. Put a relay in the middle here. So what it's doing is that if it's going this way, so then we'll have our this is more important. Basically, it's measuring current at this point. Measuring currents here, right? We're checking it with the current at this side, and then if it is very closer, it will take it like that. If it is not, it will trip the system and see that something is actually something is reducing current or increasing the current beyond what is acceptable. So that's differential protection. Now the next one is the frame earth protection. Now with the frame earth protection, so with the bus bar protection, yes. So with the bus bar protection, we talked about the differential protection for bus bars, and then we talked about the frame earth protection. So what the frame earth protection is doing is that it is measuring the fault current from the switchgear frame. So you see, we have this bus bar is a metallic bar. Usually it's a metallic bar. So you need to place some sort of covering around it, right? When you place some sort of insulation around it, right? So that the metal bar doesn't touch ground. If it touches ground, that everything is off. You understand? So it involves measuring the fault current from the switchgear frame, the frame of this one, to the earth, right? Right. Yes, so that's basically it. So it's not very complicated. It protects the bus bar from earth conditions by placing a frame around it. It's not that complicated. That's very basic. Understand? So bus bar protection, that's the two things you do for bus bar. Transmission line next. So for transmission line, you use a few different ones. The primary protection for a transmission line is your distance relay. Now distance relay, um we we have let's say we have bus A to bus B, right? And then we have our relay here, right? And we assume all the relays are forward looking. And then maybe you have to assume that your relay is a numerical relay, numerical or digital relay or electromech slash static. For numerical relay, zone A is 0.85, and for electromech, it is 0.8, right? So if I tell you that if I give you a long transmission line that is 100 kilometers, and tell you that, so let's look at the question very quickly. Here's the question. Here's the question. Here's the question. Right. So for X66K radial feeder shown below, calculate the zone 1 setting. If they don't tell you, yes, if they don't tell you, please use the 85, right? If they don't tell you, um, um assume that it's Eka relay, right? Then they give you the resistance as 0.24 is 0.8 ohms per kilometer. So with this one, if I've given you this, you have your resistance, you have your impedance here like this. The first thing I have to do is to find total impedance. And that's by multiplying the length of the wire by the impedance of the wire. Right? And that gives me, what does that give me? That gives me 24 plus 80J ohms. This is my total. Right. Now I have to find 85% of it. Right. So what I'll do is 85% of Z is equal to 0.85 24 plus 80G. I'm sorry if you don't hear me out. Please just play it again. I'm rushing so that the time has reached dicey points. Right. So 0.85 times 24. That gives me 20.4 plus 68 J. Right. That gives me the um, um, what does that give me? That gives me my zone 1 setting. Right. This is in ohms. But then this is not magnitude. So I actually have to find the magnitude by doing 4 squared plus 60 squared. That gives me solve yours actually. This one gives me ohms. Right. So this is how we solve it. Zone 1. So this is zone 1 is 0.85 or 0.8. Zone 2 is 1.2 of the protected line. So let's say that we have only one liner, 1.2 times protected line, 1.2 times protected line, or 100% of your protected line plus 50% of your shortest line, such as adjacent line. About zone 3 is equal to 1.2% of the protected line plus longest adjacent line. I hope this makes sense to you. If they tell you to find, okay, great. So that is it. And so when they say distance relay, right, you can find the zones for each of them so that if a fault appears anywhere on the line, you can work with it. You understand? You can work with it. So the primary protection for a transmission line is the distance relay. The second protection is your differential relay. Differential relay, but this one balanced voltage. Balance voltage is exactly where you think it is. Checking the voltage at both sides to make sure it is compatible. So you have a transmission line like this, and then we have CT1 here. Right? And what happens is that you have a relay here, and at first we connected it like this. Now it goes the other way around, right? What I mean by goes the other way around. So what I mean by it goes the other way around is that instead of it um eh, so there are two CTs in action. There are two relays in action. There are two relays in action, right? I have one relay here and another relay here. I'm very sorry, I don't know where my mind was. We have two relays. There's one relay here, so relay one and then relay two, right? And then you have this here. So you have this leg of the CT being connected to have this the end of the relay being connected to you have this end of the CT being connected to this relay. You have the other end connected like this. This is connected here. This connected like this. You understand? So this is what happens. Basically, what happens is that you're measuring the voltage over this line at this point, and then you're communicating to this relay. You are measuring the voltage and communicating to that other relay. And the other relays are very far apart. Right. So that's the reason why differential relay is a form of protection, but it's not really used now, right? Because they are very far apart. Then as with the circulating current or the balance current, what happens is that you're supposed to what happens is that the current is supposed to be the same or the voltage is supposed to be the same. Readings are supposed to be the same, then you're cool. The third one is that you have overcurrent protection. The relay can the relay can the relay can have too much current, so you need to protect against that. Meaning that you need to find the limit of the line. You understand? You have to find the limit of the line in terms of current, right? And then set up an OC relay there. The next one is overload overload protection. Right? The overload protection, what happens is that so we see there's a difference between overcurrent and overload. Right? One of it is that let's say that your generator or your transmission line is rated, your transmission line is no, let's see your generator because it will come to play in generator. Let's say the generator is rated 5 MVA, right? And then you as a consumer are drawing 5.2 MVA. It's not like when generators are rated 5 MVA, this is not like a final end limit that if you go a point beyond it, the generator would blow up. No, it's a rated limit. It's the limit at which the generator can run for many years without actually suffering. 5.2 can be sustained, but not for long. And then heat equal to I squared RT, right? So if, for example, I was drawing 400 A, right, with 5 MVA, and then now I'm drawing 410 amps, right? I'm drawing 410 amps. It's not really so much so high an increase. You understand? But the thing is that my system is still overloaded. So what I can do, so what it leads to, right? What it leads to is that you get a lot of heat in your distance times time. So the more it goes on, the more your heat, your system becomes more hot. You understand? It doesn't draw so much current that it can trip over current. It draws smoke like a little large, like it draws the current large. Hey, what am I saying? It draws a larger current than a rated current, right? So heat is produced in the system. So what we use for overload protection is heat sensing. That is thermistor or thermocouple. So thermistor or thermocouple protection. You understand? That's what overload protection is. Hey, what am I doing? What's overload doing here? Is everything's correct. Ignore this silly mistake. It is for the generator. So four, protection against lightning strikes. Very sorry. Protection against lightning strikes. Right. Right. You use sky wires for this. Sky or earth wires. Simple. protection against damage of line insulators by flashover. Okay, so with this one, we use arcing horns. You see that the transmission line to is actually very simple. You can do calculations for distance relay, differential, balance voltage. No, no. The calculation it's not. I heard it wasn't taught, so let's ignore that. So it's a protection, but you don't do calculations for it. Overcurrent protection. You can do this thing. You can do calculations for it. Basically, it involves just finding the limit, right? So if my transmission line is rated something, right, and then there's a voltage limiter, I can find my I rated, right? Because keep in mind that S is equal to root 3 then L I L, right? So I can find my I rated, like my line current rated. Then when I finish finding my line current, I multiply by an overload factor, like let's say overload factor, like overcurrent factor, right? So depending on maybe 1.2 something else, I multiply by that, and that gives me my like the high current for my overcurrent. Understand? So we can move on. Great. We can move on. So we are done with transmission line two. Right? Now let's go on to the let's talk about transformer. Let's talk about transformer. For transformer, so many things can happen. The generator is the one that is the most prone, like is a problem, really a problem. So let's look at transformer. So transformer is prone to a couple of problems, right? Starting with your winding flashover. So you can have low voltage, high voltage winding flashovers. You can have high voltage winding faults, low voltage winding faults. You can have interturn faults. You can have core fault, tank fault. These are the 6 types of faults you can have. These are the 6 types of faults that you can have. You understand? So let's talk about them. It's not really important, but let's run through them with speed. Right. So with the HV and LV winding earth fault, what happens is that your fault current is controlled by your leakage reactants, right? So you have a system. No, no, no. This is not important. It's not important. What is important is that to protect a transformer, what you can use is differential protection. Differential protection, right? You can use differential protection in your system. So basically, check you have some transformer here. This this is CB, right? This is CT. Charlie, what's something? Right. So this is CT1 and this is CT2. This is a CBA. This is CB like B. So if you trip only A alone, you've cut supply off, but you've not isolated the units. Like you've not isolated the units. Unit protection requires cutting off A and then B. You understand? So what goes on here is that you measure the current before it enters, you measure the current after it enters, then you just check if they're the same or generally in the same area. You are cool. Right? This will help. So what happens is that this is a unit protection. So whatever happens outside, so let's say that there's a fault current outside, it doesn't really it will affect it, right? And there's a question like that I will let us look at. Look at it. Yeah, yeah, I'll let us look at it. So that even if it doesn't come, it will help you think a certain way. Understand? Or affect it in some way. But the main protection is for internal fault, not for external fault. You understand? Cool. So this is called, as I said, this is called the differential protection scheme, but it is um, the balance current or the circulating current scheme. Beautiful. So this is the first one. This helps you against interturn faults, basically interturn faults, right? And now restricted earth faults, restricted so differential protection, restricted earth fault protection, right? So what happens is that on the HV side, on the HV side of it, so let's say you have a transformer, right? On the so this is so so one more thing, if it's a step up transformer, you know where it's high voltage. If it's a step down transformer, you know where it's high voltage. So let's assume it's a step up transformer. It's a step up transformer. So this is normal. Right? Your low voltage and then your high voltage. Yes, yeah, right. So on the high voltage side, then the residual current of three CTs is balanced against the output current of the CT in the neutral. Right. So you balance the you check the currents of this check the currents after. So you place a CT here, you check the currents after, and compare it to the currents from the neutral. You understand? And then in the LV side, hmm, I've been told it's not important. Let's move on. So we have the restricted earth fault protection. Right. Beautiful. And so these are the two types of protection that goes on in the transformer. Let's see another one more. Right. Yes, I knew it. There's a mechanical protection focus relay. So with this one, it provides mechanical protection. So what happens is that you have winding oil, and the winding oil is supposed to help cool the transformer, right? But then if there's failure in winding insulation, yeah, right, it will result in arcing. So failure in winding insulation will result in some form of arcing, right? Which would decompose the oil, right? It will separate the oil because we all know oil is like it's organic, right? So it will decompose the oil into hydrogen, methane, and some other things be like that. And so that's the first way. Second way is that if, for example, only some part of the oil is being heated there, right? There's sort of like it's like that thing that happens to glass annealing, right? Some part is heated, some part is not heated, and then the glass breaks because there's so much stress on it. Right? So you can have localized heating, which will decompose the oil into gas. You understand? Or the filler in the winding insulation will result in arcs, and then the arcs itself, right, would decompose the oil into hydrogen and then methane. So when this happens, you have like these are all gases, right? These are all gases in the system. So what happens is that the gases will bubble up to the pipe. Now, when it bubbles up to the pipe, it will be trapped at the top of the relay casing. When it's trapped at the top of the relay casing, the switch will just it will break. So basically, you have like sort of this one, and you have your relay in the middle. Then you have it here. So oil is supposed to be passing to when oil passes to no problem. But when it meets air, no. When it meets a second, like just a small pocket of air or gas in it, right? It will operate the mercury switch and then to activate the alarm circuit. You understand? So that's what happens. So that's the big possibility, and that's the last um protection for our transformer. Right? With overloading we use with overloading we use the same thing, right? So overload with overload we use the same thing. We use thermistor or thermocouple, right? Because it's a heat thing. You understand? I think that is all. That's it all. So so it mentions that we can use dial type thermometers. You understand? We can use dial type thermometers. There's no OC here, like there's no overcurrent here, right? So then um this is how we protect our transformer in our system. We use differential protection, we use restricted earth fault protection, we use the Bocos relay for mechanical faults, and we use the overload relay for heat. In okay, cool. And so we have the generator. That is next. Right. The generator is the one that is most prone to faults, right? So this one, let me use the slide. So one more thing, right? I've forgotten who said it, but they mentioned that if you are in doubt, use differential protection. Differential protection is actually the safest. So we have generator protection. Both classifications are five, right? Overload and overcurrent issue, data fault, fault, failure of prime mover, which is mechanical fault, and failure of load circuit. Use these are all the protection schemes you can use. Load, overcurrent, overvoltage, under voltage, all of these. We look at a few of them. Use generator, we use generator protection. We use differential protection, sorry. So this are state of this. I hope you see where the mouse is. So the tablet is. We have generator stab windings, right? And we place a CT before, place a CT after, right? And then we have a CB here. So if something trips now, if something is wrong, we tell the CB to trip. Beautiful. So differential protection protects against winding insulation failure, failure of field circuit, or the prime mover failures. You understand? Failures is mechanical failure of field circuit, and then winding insulation failure. So that is the either rotor or stator. Help protect against a lot of things. You can ignore all of this. This is not important at all, right? See, these are the protections that we can have. To mention it, mention it out. So we have differential. So you've seen it. We have differential protection for one. We have one that we can have is earth fault protection. That's it. Earth fault protection. So how this is done, so we know how differential protection is done. How earth fault protection is done is by using a transformer, right? So this actually, so it's just helping the explanation go down some. One winding of the transformer, second winding of the transformer. Have a circuit here. Then we have this is our relay. Then we have a loading resistance. Right. So what how this works is that we apply we use a transformer, right? And then we adopt a relay system. So we use a relay system to measure the earthing transformer secondary current. We are always measuring the secondary current, or we connect a voltage operated relay. So it's 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 basically like you're constantly measuring the secondary the transformer, yeah, its secondary current. And the second it goes up or it goes down, which is an indication of earth fault, right? Meaning that something is connected to ground somewhere. Right? We know that we need to the generator needs to trip. You understand? Okay. So that's how we do earth fault protection. Now overload protection. Overload protection, same thing. Right? That's what I explained for the transmission line. Overload protection, we use a thermistor or a thermocouple, or we use a thermometer. Right? Maybe dial type thermometer or something like that. Overcurrent protection, right? We use the IDMTL relays. You understand? That one to us. What we have. We use the relays. We can do calculations for it. You understand? So what if I think there was one in. If it is, I'll just put it in the class group. I don't have time. If we have overcurrent protection, basically checking if the current that is being produced is too high. If it's too high, it would break the circuit, right? And then the rest of them, none of that, the rest of them are not really that important. To, yes, okay, let's look at rotor fault, how we go against rotor fault. Rotor fault, there are three different ways of protecting against it, right? We can use the potentiometer method, the AC injection method, or the DC injection method. I truly don't think you mentioned it in class. You didn't mention it in class, so we are good. Potentiometer, so you can just mention it, right? But these are the things that your generator, these are the important things that your generator would have to undergo to understand. So let's move on to industrial motor and our normal loads. Okay, so the rest of the protections, I think the book does a really better job. It does a really good job. So let's look at the book, right? So for protection schemes in buildings, we look at the lightning protection systems. You understand? So you have a couple of yes. So you have your arrestor, your lightning arrestor. You have conductors that are conveying the currents to the earth. Then you have earth leads, electrodes, and then um links between all metallic frames and then earth leads. So what happens is that you want a very very high metallic what do you call it, a metallic device, right, to capture lightning and then send it directly down to earth so that the building is not affected. You understand? Right? So there are three types of building protection system. The simple lightning rod, right? So you have a metallic capture tip, right? So it's a lightning rod like it's just a metal wire that has a very, very spiky top, right? That is placed at the building, and then it is earthed by copper strips. And so you have lightning rod with taut wires. Wires are stretched, so you have some wires that are stretched above the structure, and it catches the lightning in the sensor down. You understand? And a lightning conductor with meshed cages, Faraday cages, right? So protecting the building itself cannot have any, like you can't bring foreign signals outside there. The mesh cage will catch it. So that's basically that. So you place numerous conductors symmetrically all around the buildings. Used for highly exposed buildings, sensitive installation. You understand? Yeah. So that is that's how the building protection system is. Now you have electrical installation protection system. Right? So let's say you have some electrical installation in your building. I don't want to say this thing, but I don't see um uh, um like you have a substation that is inside. I've forgotten what like you have a substation inside a house or something. Hey, forgotten what it's called, but it's fine. So how you what the what we didn't talk about this in class, so we can. So but however, right? However, um it's basically the same thing. You understand? You have some lightning, some connector upstairs, connector on top of the building, very high above the building, that captures the um, lightning and sends it to earth. You understand? So overcurrent or earth fault protection, right? So the two types of overcurrent, at overload and then the short circuit. You understand? With the overload, it's up to like 3 times the normal current, and then with the short circuit, it's more than that, 10 to 100 times. It's so you use a fuse or a circuit breaker to protect against overcurrent, and this is where your calculations will come in. So if you have the calculations that you have like that leads to something like this thing, right? Where your device is sitting here, no, right? Use this is where your calculations will come in. It is for your overcurrent protection. You understand? Okay, cool. Now, earth leakage protection. So it is possible for the metallic frame to be live due to insulation failure. So you use something ELCB or RCD, right? Earth leakage circuit breaker or residual. Hey, yes, RCD, residual current device. Right? You use either of them, right? So it's a circuit that has an inbuilt relay to detect current. It has an inbuilt relay to detect current leaking to earth from an installation and then cut off power. You understand? It may be voltage or current operated. So basically, sorry. So basically, check whether there's some current that is leaking to earth, right? Like by measuring the current in the earth wire and then just very sorry. I'm getting so many calls. It's not me. It's YouTube. It's YouTube. So back to it. Yes. Let's try now. So protection against electric shock. The electric shock to basically the same thing. So the limit is it's I think the limit is one amps will kill you. That one I know. The limit is around 100 milliamps. Right. So protection schemes against that. So physical prevention of contact with live parts with barriers, insulation, or inaccessibility by using screws or something to make sure that you don't actually touch parts that are live. You understand? In additional protection, you use RCD or the earth leakage circuit breakers. Understand? So the two levels of protection measures exist against indirect contact. So for example, let's say that you touch something that is connected to a live wire, of course it will shock you. But there's indirect contacts too. So what you can do is that you earth all exposed parts, right? And then you automatically disconnect the supply of the section, right? So that like at any time that anything breaks the circuit, no, you would like you will trip it. You understand? So RCDs detect leakage current, right? It detects leakage current, operates within 25. Yeah, so it measures the current balance between two conductors using a differential current transformer. So basically, the uses the current a differential relay to check the difference between like what is coming and what is returning. You understand? So there's a live current flows through live and comes back to neutral. So measures what is going through live and measures what is coming to neutral. And if they're not the same, there's a leakage of current, it will open. You understand? Beautiful. So that is how we protect buildings. Right? And then the need for motor protection. We know why motor protections are necessary. Right. So we have um, unbalanced supply. So supply is not balanced. So let's say that one phase is. Yes, so finally, nice, finally. So you know what the need for protection is. The types of fault, unbalanced supply, under voltage, single phase, and reverse phase sequence, bearing failure, finding fault, overloads. I think yes, so the protection schemes for induction motors, overcurrent protection, right? You have overcurrent protection, and this one it is provided by overcurrent relays with C fuse. So you can calculate what the highest level a motor can go, and that one you know how to. It's what's the highest current in the motor, right? Normal rated current and set overcurrent relays for it, or you can do fault analysis and then use that current level for setting of your OC. For overloads, right? You need you know what overload is, right? Because it's giving the motor too much work to do, right? You want to set up like it's giving the motor too much work to do. So then the current that is drawing is a little higher for long periods of time. It's not fault current, right? It's so high that producing a lot of heat because heat is equal to I squared RT. You understand? So the more the time goes on, higher the heating. So then what you want to um, do you want to use a bimetallic strip, right? That expands with heat, and then the contact. So how this is have one strip being some other material, some other strip being some other material, right? So the second that there's too much in the system, one starts to bend. So let's say that there's a contact here, there's another contact here, and then it's connected to one of the contacts. Let's say that you have it here, you have another one which is down. So one starts to expand when there's too much, then it touches one contact, and then you shut off the motor. So that's exactly how. For phase imbalance, what you do is use unbalanced relays or like use unbalanced relays of relays which are out of balance. Use stalling. Installing it refers to a condition where the motor is unable to. With phase unbalance, it's like sorry, with phase unbalance, it's like you have one phase being higher than the other one, or you have one phase that is totally off, and other phases are on. To understand, causes something else. So use unbalanced relays. Just mentioned unbalanced relay. For stalling, it refers to a condition where the motor is like unable to operate. Right. So use the thermal relay. Right. So the thermal relay is your overload relays. You don't use no, you don't use thermal relay. This one, I think you can't really go in depth. So yes, single element stalling relay, single element stalling relay, and a speed measuring relay too. Insulation failure. Insulation failure. We all know what insulation failure is. When your insulation around is subjected to so much stress that it breaks down and starts to act as a conductor. You understand? Sorry, oh. Okay, that's fine. Okay, sure. So we use an earth fault relay, right, for use an earth fault relay for insulation failure. For differential protection, for serious faults, differential protection, you understand. So loss of supply. Loss of supply too is basically the same. I think loss of supply use under voltage relays. Loss of supply under voltage relays are used for. So that was for induction motors. For synchronous motors, it's basically the same thing, right? But you need to add loss of synchronism to the system. Loss of synchronism use an out of step relay. Most everything is the same. You understand? Yes, beautiful. Thank you. Any questions? Please put it in the group. Sorry for it being so late and it being so fast. Right? We had electricity, had other issues on top. Thank you.